5. Um, and this one, yeah, I kind of set you up to fail on this one, but we'll go through it. So what we've done so far is we have done part B. So we have done problems so far where you calculate the acceleration of something that's on a cowboy as it rides a horse around, but we've always put the origin at a fixed point. Okay. So now when we get to, I'm going to do B first. That's the easier one. And then I'm going to go back and do A. And when we do part A, we're going to put the coordinate system at the spot that's shown over on the left. Okay. And what makes that more confusing is the origin is in circular motion, and circular motion has acceleration. Okay, and so this origin is not only is the coordinate system or the axes changing orientation, but the origin is also accelerating. Okay, so we're going to have to use relative motion, and we're going to have to use the rotating coordinate system stuff. Okay, and when we do this, what we better get is an acceleration using this origin that matches the acceleration using this origin. Okay, those two answers have to agree because those are both accelerations that you need to be able to put into Newton's second law.
So again, regardless of the origin, any problem will be the same?
Yes, that's right. I mean, accelerations just, they have to be the same because the forces don't change, you know, and so Newton's second law says the acceleration better be the same.
One approach is just easier than the other.
That's right. So if you have the choice, you always want to put the origin at a fixed point so that it doesn't have acceleration. But if you don't have the choice because you have a mean constructor, then you got to do what you got to do. And these are not things, by the way, that I ever put on test, the things where the origin is accelerating. But I do think it helps give you kind of an understanding of what's going on. So I think it's worth paying attention to anyways. Okay. So, this is the horse. This is the cowboy. What's the main distinction there? Like, how do you decide which is which?
The acceleration, the motion of one can affect the other.
Yeah, and it's really what you want to think about is the axis of rotation. So does the motion of one change the axis of rotation of the other one? Okay, moving that arm up and down doesn't affect the axis of rotation of the disc. That's still along the y-axis, right? But rotating that disc 10 degrees changes the axis of rotation direction of the arm, okay? And we want to calculate the acceleration of a point here in both of these. So I'm going to do B first. And the acceleration of that point P is equal to the acceleration of P that's observed in the coordinate system plus the angular acceleration of the coordinate system crossed with the position vector. plus 2 times the angular velocity of the coordinate system crossed with the observed velocity of that point P plus capital omega cross P. And now we're just going to go and collect these things. Okay, we have 1, 2, 3, 4, 5 things to collect always. Okay, so let's see. Angular velocity. So the disk has an angular velocity of -5 about the y-axis and an angular acceleration of +10. That coordinate system is rotating with the disk. So that angular velocity and angular acceleration of the disk is the angular velocity and angular acceleration of the coordinate system. So capital omega is 0, -5, 0. And the angular acceleration of the coordinate system, or capital omega dot, is equal to 0, +10, 0. Any questions about that? Okay, at this instant, because remember, we're always doing this at a single instant, the position vector of P. Now, let's think about that. Well, the position vector goes from the origin to the point that you care about. So that's going to be, let's see, the radius of the disk is 1.5, the length of the rod is 1.3. So from the origin to P, we have to go 1.5 in the negative x direction to get to the hinge, and then 1.3 in the positive y direction to get to P. So this is -1.5, +1.3, 0. Anybody have any questions about that? Okay, so that's easy collecting. Those 3 are collecting seashells at the beach. But the next 2 are harder, like collecting Maseratis or something, you know. So we have to calculate the velocity of that point P that's observed by the coordinate system. That's the first one we need. And how are we going to, so think about if this, so now we're thinking about what that coordinate system sees, okay? And so you can forget about the motion of the disk. The coordinate system doesn't see any of that. So if that disk is just fixed, what does that coordinate system see as the motion of P? Can you visualize that?
No, it's the beam moving down, but it's also not at the.
Yeah, it's just all this coordinate system sees, for all it knows, there's nothing going on except this thing moving like this. And so that point P is just moving in a circle, okay? Whichever way it's rotating, but it has to be a circular motion, and that axis of rotation has to be parallel to Z, either this way or the other way.
Okay. So the observed velocity is the same as if it would be observed from the pin of the beam, or different?
It is the same, yes, it is the same. And that's because vectors don't have a location, they only have direction and magnitude.
Okay.
So when you're talking about velocities or accelerations, where the origin is doesn't matter.
So it would only be different if the axes weren't in the same direction, or weren't parallel.
That's right. Okay, so what we're going to do here, since we know this is circular motion, well, we have a formula for the velocity in circular motion, and that is lowercase omega crossed with the r vector. Okay, well, we just dealt with capital omega and the p vector, so you got to be real careful here that you're talking about the right lowercase omega and using the definition of the r vector. Our lowercase omega, Well, we're talking now about the motion of the cowboy. And that has a constant angular velocity of 8 radians per second. You can see that it's about the z-axis. Anybody ever have any questions about how I identified that this arm is rotating about the z-axis?
No, the pin is parallel with the z-axis.
Exactly. That's the way to think about it. Yep. So this is 0, 0, positive 8. And now someone tell me the definition of the r vector.
The center of a circular motion to the point of intersection.
Exactly. Perfect. So the r vector now doesn't go all the way from the origin. It only goes from the center of the circular motion, which is the hinge right below, at the bottom of the arm. And so the r vector is just 1.3 in the positive y direction. So this is 0, 1.3, 0. And so the velocity of p that's observed in this coordinate system is 0, 0, 8 crossed with 0, 1.30. And that is 10.4 in the negative x direction. Any questions about that? Okay, so we collected our first Maserati. This is an easier one to get, but now we're going to collect the hard one. I don't know what years are good for Maseratis, but now we're collecting the rare one. So now we have to calculate the acceleration of that point P that's observed. And again, the observed velocity and acceleration, this is just circular motion. So here we're using the watermelon equation. All ripe watermelons will rot. And this body, the arm, has a constant angular velocity, so alpha is 0. We already know what omega and r are. So the acceleration of p that's observed is equal to this thing that goes away, plus 0, 0, 8 crossed with the quantity 0, 0, 8 cross 0, 1.30. Come on. Okay, so this is negative 10.4 times 8 in the y direction. So that is 0, negative 83.2, 0. All right, well, we can sanity check both of these because these are just simple circular motions. It's easy to figure out what's going on. So this is moving. This is rotating about the positive z-axis. So it's going this way, which means the velocity vector needs to be in the negative x direction. Okay, is that what we got? I don't know my paper in front of me, but hopefully that's what we got. And then what about the acceleration? Well, in this case, it's a constant angular velocity. So there's no tangential acceleration. So all we have is centripetal. And so this should be in the negative y direction toward the center of the circular motion. And that's what we got. So, that didn't verify the numbers, but it verified the component and the sign of the component. And now it's just a matter of putting everything together. So our acceleration is equal to the observed acceleration plus the angular acceleration of the coordinate system. So 0, 10, 0. Crossed with the p vector, negative 1.5, positive 1.30, plus 2 times the angular velocity of the coordinate system. And actually, you have to be so careful with this stuff. I mean, I just pulled it up here and saw this lowercase omega. I was about to put that down, but this is the angular velocity of the coordinate system. So I want 0, negative 5, 0. Crossed with the observed velocity, which is negative 10.4, 0. And then plus capital omega, 0, negative 5, 0. Crossed with the quantity 0, negative 5, 0. Crossed with p, which is negative 1.5, positive 1.30. And now of that point p is equal to 37.5, negative 83.2, and then 89, negative. Okay. Anybody have any questions about that? So if then you needed that acceleration for Newton's second law, this is the acceleration you would have to use. Now we're going to do part A. And part A is tricky because the origin is accelerating. And you deal with accelerating origins using relative motion. Okay, so I'm going to give these names. I'll call this point is the ground, the fixed point, because it's fixed to the ground. I'll call this A, and then we're calculating the acceleration of P. And the acceleration of P relative to the ground is equal to the acceleration of P relative to A plus the acceleration of A relative to the ground. So let's think about what those things mean. The acceleration of A relative to the ground, we've done that problem a million times. That's just a simple circular motion problem as this point A goes around G. So we'll do that separately. That's circular motion. What's the meaning of the acceleration of P relative to A? That's the most important thing you need to think about with this. Okay, what does that mean? And what that means is all of these rotations are still happening the same, but we're going to treat it as if A was the fixed point and everything else was rotating around A. Okay, so like imagine that this is gone and this whole disk is just rotating around A as this rotates around the hinge. Okay. So this one is circular motion of A around that point G. And this one, we're going to have to use the rotating coordinate system equation. Okay? Then we'll add those two pieces together at the end. We might as well do the easy one first. So the acceleration of A relative to G. That's just a circular motion problem, and we're going to use the watermelon equation. Well, the body that's rotating in this circular motion is the disk. And so it has an angular velocity of, so this disk for the circular motion is the same as what my coordinate system was for the last part of the problem. So we have 0, -5, 0, and 0, 10, 0. So this is 0. Which one is which, though? Okay, 0, 10, 0. Okay, so 0, 10, 0, 0, -5, 0. And then R is the vector from the center of the circular motion to the point of interest. That is the vector from G to A. So that is -1.500. So the acceleration of A relative to G is equal to 0, 10, 0, crossed with -1.500, plus 0, -5, 0, crossed with the quantity 0, -5, 0, cross -1.500. And so this acceleration of A relative to G is 37.5015. And we'll put this aside and come back to it. Okay, so what we've calculated here is the acceleration of A relative to G. And now we have to calculate the acceleration of P relative to A using a rotating coordinate system approach. Okay, so acceleration of P relative to A. This is going to be the rotating coordinate system stuff. So this is going to be the acceleration of P that's observed. But this time it's observed by a different video camera. This time it's observed by a video camera that's at that point A, not at the point G. Plus capital omega crossed, capital omega dot crossed with P, plus 2 times capital omega crossed with the observed velocity vector of P, plus capital omega cross quantity capital omega cross P. Okay, these P's are going to be different now because the origin is different. Remember, what's the definition of the P vector?
The point of interest to the origin?
Origin to point of interest. But yeah, so if either one of those changes, that P vector changes. And now we have to collect this stuff. So let's collect the seashells first. So the angular acceleration of the coordinate system. Okay, so this coordinate system, when we did part B, was rotating with the disk. Now we've moved it to a different spot on the disk, but it's still rotating with the disk, okay? It's still rotating with the horse. So none of the angular quantities change when you move something around on a body. A single body always has the same angular velocity, same angular acceleration. It's not dependent on the point on the body. Okay, so this is going to be 0, negative 5, 0. Oh no, 0, 10, 0, and 0, negative 5, 0. 0, 10, 0. And capital omega is 0, negative 5, 0. And then the last thing that's easy to collect is the position vector. That's the vector that goes from the origin to the point of interest. Well, now, before that was from G to P. Now the origin is at A, so that's just going to be 0, 1.30.
So the duration on the angular acceleration at point A is the same as the again?
Yeah, think of angular acceleration and angular velocity as belonging to a body, not a point. So since we're still on the same body that we were in the previous way of doing this, those have the same values. But whereas regular velocity and regular acceleration, those change as you go from point to point on a body. Okay. You've seen that from, I don't know, maybe you haven't, but they used to have these death traps called like carousels that were made out of like 1,000 tons of iron, and it would spin around on this axis and you'd try to hold on,
They don't have those now?
They don't have very many of them. I know where one is, but okay, so on those things, if you remember, if you've been on them and you remember, like if someone's trying to throw you off, you're trying to get to the middle as fast as you can. If you can get to the middle, there's no acceleration. All you're doing is spinning around. And you can stand there forever. You don't even have to hold on to anything. But if you're on the outside, those accelerations are big, So acceleration depends on where you are on a body. Angular acceleration does not.
Neither angular velocity, right?
Exactly. Yep. Okay, so we got these. Now we have to collect the Maseratis. So velocity of P that's observed in the coordinate system. This is just a circular motion. So this is omega cross r. And we have to collect some little things for this too. So this angular velocity omega is the angular velocity of the arm. And that was 0, 0, positive 8. And the r vector goes from the center of the circular motion, bless you, to the point of interest. That's 0, positive 1.30, which this time matches the position vector. Sometimes it does, sometimes it doesn't, depending on where the origin is. So 0, 0, 8. No, that's what I just did. 0, 1.30. Okay, so the velocity that's observed is 0, 0, 8 crossed with 0, 1.30. And that comes out to be negative 10.4 0, 0. And now we have to calculate the observed acceleration of p. That's the watermelon equation. So we got alpha cross r plus omega cross quantity omega cross r. That arm has a constant angular velocity, so this one's 0. And so this is 0, 0, 8. I'll just put in the omega cross r that I just used. So this is cross negative 10.4, 0, 0. And I know I already calculated this, but I don't remember.
Negative 83 point.
Yeah. So 0, negative 83.2. 0. And now we have all the pieces that we need to calculate this. So the acceleration of p relative to a is equal to the observed acceleration, 0, negative 83.2, 0, plus capital omega dot, which is 0, 10, 0, crossed with the position vector, 0, positive 1.30. You can see that this one goes away because those two are parallel to each other. Plus 2 times 0, negative 5, 0, crossed with the observed velocity vector, negative 10.4, 0, 0, plus angular velocity of the coordinate system, 0, negative 5, 0, crossed with the quantity 0, negative 5, 0, crossed with the position vector 0, 1.3, 0. And this one all goes away because these two are parallel. Come on. My computer really wants me to get the news right now. So important.
America got rich and got sad.
That's what they want me to know. That's important.
Know that already.
Exactly.
Or not that got rich, but
Yeah. Yeah, I think the part of America that got rich hasn't gotten too sad. It's just the rest of us. Okay, so acceleration of p relative to a. So what do we have here? 0, negative 83.2, 0, plus this third term, what's that called?
Coriolis.
Coriolis acceleration, yeah. So that one is 52, so 104 in the negative z direction. So 0, 0, negative 104. And so here we go. 0, negative 83.2, negative 104, and Does it match what we got in the first one?
No.
No. Ah, damn it. But wait. Remember the relative motion part. So now add on the acceleration of A relative to G. And what we get is that the acceleration of P relative to the ground is equal to 0, negative 83.2, negative 104, plus the thing 37.5015, positive 15. And what we get is 37.5, negative 83.2, negative 89. Does that match what we got on the first one?
Yep.
Okay, that's stressful because a lot of little sign errors and stuff can happen when you do these, but we got the same thing. Okay, so if you have to use an origin that's not fixed, then you have to use relative motion. But this, really the main reason that we went through this is to remind you that when you have the choice to put your origin at a fixed point, it benefits you to do it. Okay. All right. So I want to put a problem up, and you can get in groups or do it by yourself. But I would definitely recommend, as you go through the steps, compare answers to people and stuff. But we're just sort of all together going to go through one of these problems. We're just trying to get familiar with all this, sort of ingrain the steps in your head. So here's the example, and it actually looks very similar to the one we just did. So we have an arm like this, and that arm is connected to a disc and this is the point P, and we are going to have the disc rotating at 20 radians per second like this. And then the arm is going to rotate on top of that disc at 40 radians per second and at 100 radians per second squared. And we want to calculate the acceleration of that point P. Okay, so before we start working on stuff, let's just sort of assess this, what's going on here. Which one of those two bodies is the horse? The disc, yep. And so the coordinate system is going to be fixed to the disc. Our last decision we have to make is where that origin is going to be on the disc. So where do you want to put the origin of that coordinate system? That would be the harder choice, and in the middle, because it's a fixed point. Okay. So we want to put the origin here. Okay. If we put it at the bottom of the arm, then that point would be accelerating and we'd have to use relative motion. It's not the end of the world, but it saves you a lot of time to put it at the fixed point. Okay, well, so I'm just going to give you some time, and then I'm going to go through it after I give you time to work on it, and then you can go back later and compare your steps to mine, and if there's anywhere where you got off track, that can help you spot, you know, things that are hazy or whatever. Yes?
Can you give us the radius?
Oh, you have to calculate that. No, just kidding. Yes, the arm, the length of the arm is 0.02. So this is all very small scale. That's 2 centimeters. And the radius of the disc is 0.01 meter. And then we'll call it a day. So the acceleration of that point P is equal to the observed acceleration of P plus capital omega dot cross P plus the Coriolis acceleration, 2 times capital omega crossed with the observed velocity of P plus capital omega cross quantity capital omega cross P. And now we'll make our collection. So our omega dot is 0, 0, negative 100. You know it's negative because of the right-hand rule. So if you put your fingers in that rotation, your thumb is in the negative z direction. Your capital omega is also in the negative z direction, but that's 0, 0, 40, negative 40. And then your position vector is from the origin to the point of interest. So that is 0.01 in the positive z, and then 0.02 in the positive y. Any questions about any of those? Those are the easy ones to collect. And then the observed velocity is equal to lowercase omega cross r. So this, now we're just talking about imagining the disk being still and the motion of the point P in that circle as the arm goes around. So the lowercase omega is the, I did this wrong. My P is right, but I was looking at the, so my coordinate system shouldn't be fixed to the arm, it should be fixed to the disk. And so this should be 0. Come on. 0, 0, 0. This one should be, the right-hand rule says that this 20 radians per second is in the positive y direction, so 0, 20, 0. And now we're talking about the motion of the arm. So omega for the arm is 0, 0, negative 40. R is the vector from the center of the circular motion to the point. So that is just 0.02 in the positive y direction. And so that observed velocity is 0, 0, negative 40, crossed with 0.020. And so that is 0.800. And now we'll calculate the acceleration that's observed. And we'll use the watermelon equation. The only new thing that we didn't already find above here is alpha, and alpha is equal to 0, 0, negative 100. So the observed acceleration is 0, 0, negative 100, crossed with 0, positive 0.020, plus omega, 0, 0, negative 40, crossed with omega cross r, which we already know is 0, 0, negative 100. We already did that. And so this is
Is it
two.
Wouldn't that be the radius?
Oh, I looked at the wrong thing. Sorry, you're right. It is 0.800. Yeah.
For the R vector, which has the 0.02 in the y.
Yeah.
Would there also be the 0.01 positive z because it's the radius from?
That would be if we're calculating the p vector, but right now we're just using the r vector. So the p vector here has it, but the r vector is just from the center of p's circular motion to the point.
Okay, so then we're not considering the points just at the base of the
Yeah.
arm.
Because that's the center of the circle. Yep.
That's when we forget about the slope.
Yeah. So, okay, so this gives us 2, 0, 0, I think. And this one gives us 32, negative 32 in the y direction. And so this observed acceleration comes out to be 2, negative 32, 0. And now finally we can put all these pieces together. So the acceleration of p is equal to 2, negative 32, 0, plus capital omega dot cross p. Our capital omega dot is 0. So this thing goes away. Then we have 2 times omega, capital omega, which is 0.20, crossed with the observed velocity, which is 0.800, plus capital omega, 0.20, crossed with the quantity 0.20 cross p, and p is 0.02.01. And so all together, the acceleration of that point P is 2, negative 32, negative 36. So the middle one up there. Anybody have any questions about that? Okay, so if you got a different answer than that, I would recommend just taking the time to find where your solution deviated from this, there's a good chance it's just some dumb mistake or whatever, and that's not a big deal. But sometimes if you can pinpoint the place where you make a mistake, that can help you find something that wasn't clear in your head, So that can be a useful thing. Okay, that's all. Goodbye. It is Monday, I think that's the 11th, yeah, at 11 o'clock. And it's a plan on 2 hours.